We present center-based 3D object detection and tracking. This is joint work between Tianwei Yin, Xingyi Zhou, and Philip Cranville. I'm sure by now most of you will have seen an autonomous vehicle like this. Its core piece is the 3D LiDAR sensor up top. It measures a sparse point cloud around each vehicle, from which we can infer the location of other vehicles, pedestrians, or other driving hazards. Now this might seem like a daunting task, given that most of us couldn't do this by just looking at this point cloud. But let's see how our vision algorithms fare. We first project this point cloud into an overhead map view. From there, we use a standard 3D convolutional backbone to infer a dense feature map over the entire map view. And then we apply a standard anchor-based detector to find all the objects. Now this works well if the output objects well align with the anchors. However, it starts to break down if the vehicle starts to turn, and now all of a sudden, all the outputs are oriented at an angle to the anchor boxes. Now, our idea is to not use anchor boxes, instead representing all objects as points. Now these points are rotationally invariant. If the vehicle turns, a point will still stay a point. Now we locate all the points at the 3D center of the vehicle's bounding box. And then we infer all other properties from a feature at that center location. Now let's see how this works in practice. We start with a 3D point cloud. We voxelize it and feed it through a 3D convolutional backbone. And then we use a couple of convolutional layers on this map view feature map to infer a heat map. Now each peak, each local maxima in this heat map corresponds to an object in the scene. And features at these peaks help us infer the size, orientation, and velocity of each of the objects. Now for the velocity estimate, we do require multiple sweeps of LiDAR to get a stable estimate. But once we have that, we can get tracking for free by simply following objects back through time using their velocity estimate and matching them to one another greedily. Now we evaluate our approach on the nuScenes and Waymo dataset. On nuScenes, simply switching out anchors and replacing them with centers gives us a 4 MAP boost. On Waymo, the results are similar. For vehicles, we get a slight boost, and for pedestrians, we get a massive 8 MAP boost. Now let's look at the improvement for vehicles in a bit more detail. First, we'll break it down by rotation angle. If the output is oriented almost perfectly with the anchor box, meaning 0 to 15 or 15 to 30 degrees, there's really not much a center-based detector will give you. However, for outputs that are oriented at a 45-degree angle, which is the last column here, it can give you an up to 6 MAP boost by just replacing the standard anchors with center points. Now a similar trend can be seen if we break down the results by size. For average-sized objects, an anchor is a fairly good fit, and hence there's really not much a center-based detector will give you. However, if the object is smaller than the anchor or much larger than the anchor, a center-based approach works much better. Finally, we also rank competitively on the nuScenes leaderboard, especially considering that our entry is a few months older than most other entries on this leaderboard. Moreover, more than half of the entries in this leaderboard use center point as their backbone detector. Code and model are available online, and we're happy to answer any questions you might have at our poster session. Thank you.